the form of the Fourier transform. Oh, good. Our conference is being recorded. What you see here is the form of the Fourier transform in its continuous integral, and the form over here that we use it for measuring NMR data, which is collected as discrete points. And we have a function that we want to transform, this little x function, and to form a particular point in the transform, we multiply our function, which is a time series, with the exponential of a complex argument. And it always puzzled me. What could it mean to take the exponential of an imaginary number? And then I thought about it and think about ordinary real numbers. Let's say if we raise a real number to a power, like 2 to a power, we'll get 2 and 4 and 16 and so on. But if we raise an imaginary number to a power, integer powers, let's say, we get an imaginary number and then a positive or negative real number, a negative imaginary number, and so on. So these functions of imaginary numbers will naturally oscillate between real and imaginary values and positive and negative values. So whenever you see functions of imaginary numbers, you should instantly think oscillation. So there's nothing imaginary about them, really. They are quite physical in nature. Why do we use them in NMR? Well, we're talking about frequencies in NMR, and one way to represent frequencies is to consider orbiting particles. And we can establish all the parameters about a particular frequency by considering an orbiting particle. And the size of the orbit corresponds to the amplitude of the signal, and the speed at which the particle orbits corresponds to the frequency. But now, why do we care about real and imaginary data? Well, let's consider the two cases where we have an orbit that goes in one direction compared to an orbit that goes in another. If we only consider one component of this motion, we can't tell the difference between a clockwise and counterclockwise frequency here. It's only if we consider both components, and these are what correspond to our real and imaginary data that we measure in NMR, that we can distinguish between these cases of positive and negative frequencies, that is, orbits that are either clockwise or counterclockwise. But for the rest of the discussion, we're going to hide the imaginary parts of the data, just as long as we know that they're there. So the Fourier transform, in the form that we use it, multiplies domain data, which is this x of t, by a series of Fourier terms, which is a real part, which is a cosine, and an imaginary part, which is a sine part. And those are shown here. So here's the real Fourier term in purple, and here's the imaginary Fourier term in yellow. And to form the Fourier transform, we step through each of these Fourier terms, and each one of them corresponds to a different frequency point in the corresponding spectrum. So that's in way of background. How does the Fourier transform actually do its work? Well, let's start with this time domain data that we'd like to transform. And in this particular example, I've chosen a time domain signal that has no decay and no noise. So if we'd like to transform this particular signal, how do we do it? What we do is to form one point in the Fourier transform, we multiply our time domain data with the corresponding Fourier term, and that forms a product. Now, in practice, this is happening with complex data, with real and imaginary data. We're only going to look at the real part of these results. So we have a Fourier term multiplied by time domain data, and that forms a product. And in the examples that we see, I'm going to monitor the amount of positive and negative data in these products by a little bar chart on the side of here that will show us the total amount of positive data and the total amount of negative data. Generally speaking, when we multiply two sine waves together, the product will have equal amounts of positive and negative intensity. And so if we add up all the points in this product, we'll get something that's more or less zero. So that when we actually step through all of the Fourier terms to form different points in the Fourier transform, in most every case, the product of the Fourier term and our time domain data has equally balanced amounts of positive and negative intensity. So that when we add up all these points in the product, we get something that's more or less zero. And it's only in the cases where the frequency of the Fourier term matches a frequency in the time domain data that we get a product which is predominantly positive or predominantly negative. And therefore, when we sum up all the points, we get a peak in the corresponding position in the spectrum. It's so simple and beautiful. That's how the Fourier transform works. It matches frequencies in the Fourier terms with frequencies in the time domain data to generate them that we can look at and easily interpret by eye. But what happens in the special and typical cases that we see in biomolecular NMR, where in a particular indirect dimension, we can often measure only a limited amount of data and a limited number of points? So let's consider a case like that. The same signal that we saw before, but this time it's truncated. We only measure the first part of it. The same Fourier transform mechanism applies. We take a Fourier term, multiply it by our truncated time domain data to form a product, and then we add up all the points in that product to form a point in the Fourier transform. But in this case now, since we have truncated data, we have a limited amount of data, the cancellation between the positive parts and negative parts of the product is not so effective anymore because we don't have a whole lot of data for all the cycles of the sine waves to cancel each other out nicely. And so the result is that we get a corresponding spectrum that has these very large regular truncation artifacts, these truncation wiggles, and the corresponding signal is very broad. And this is ironic because in this case, there's no decay in the signal and no noise. But nevertheless, we get a broad signal and these large truncation artifacts. That's a problem. Now, the most common way to help alleviate this problem is by the use of digital filters, what we also call window functions or apodization functions in NMR. We multiply our time domain data by a particular function, and depending on the function that we choose, we can either broaden the data to reduce the artifacts, or we can sharpen the data at the expense of increasing the artifacts. So this gives us some options and opportunity, but the situation for biomolecular NMR and its importance can be emphasized with this particular illustration. If we take, say, 32-point signals and reconstruct them with the Fourier transform, we get line shapes like this. However, if we take only 8 points of that exact same signal, we get corresponding spectra, as we've seen, with very huge line widths and much larger truncation artifacts, even though the underlying signal itself is exactly the same. So this is a problem because what it means is the shape of the signal that we see in the spectrum has more to do with how it was reconstructed rather than any natural property of the signal itself. So that's a problem. We don't want to see peaks in our spectrum that have a shape just because of the number of points we acquired and the Fourier transform. We want to see peaks in the spectrum that actually correspond with the natural properties of the original signal. And if the original signal doesn't decay, we want to see sharp peaks in the corresponding spectrum. There have been several different ways that people have addressed this problem. In biomolecular NMR, the workhorse of helping to improve this situation is linear prediction. And linear prediction improves the situation by adding a collection of synthetic points to the original experimental data. And if we have more points to Fourier transform, these artifacts associated with the Fourier transform that we've seen are not as severe. So the way we use linear prediction for this extrapolation purpose is a two-step procedure. In the first place, we make a linear prediction model, and in the second place, we use that model to add synthetic points to the corresponding spectral data. The linear prediction model works by taking a collection of adjacent points in the original data and finding coefficients for those points such that when we multiply those points by these coefficients and add them up, we predict the next point in the measured time domain data. So in other words, the linear prediction model says that we can model one point in the experimental data as a linear combination of the previous points in the data. And so the first part is to build up a set of equations where we extract, let's say in this example, a set of 4 coefficients such that when we use these 4 coefficients on the first 4 points, we predict the 5th point. When we use the coefficients on the next 4 points, we predict the 6th point, and so on. And that leads to a set of equations like this that we can solve with ordinary linear least squares problems to extract the optimal values for this set of coefficients. And then once we have these coefficients, we can multiply them by the last points in the measured data to form a linear combination which predicts a new synthetic point that we can add onto the data. Then we can slide over the set of coefficients and use that new synthetic point with the points that come before it to make a linear combination which predicts yet another synthetic point in the data. And we can slide the coefficients over again and use these 2 synthetic points and the previous points to predict yet another synthetic point in the data. And we can keep doing this as long as we want. Once we have these coefficients, we can add as many synthetic points as we wish to the end of the data. However, you can imagine that if the experimental data has any noise in it, then the corresponding coefficients will not be perfect. And so, as we continue to add more synthetic points that are based only on previous synthetic points, any noise in the experimental data and uncertainties in these coefficients is going to be amplified each time we add new synthetic points. So in practice, we use this linear prediction approach to no more than double the size of the experimental data. In other words, we don't want to have more synthetic points than we have original measured experimental points. And in practice, this linear prediction approach is often really nice. Here's one example of what it looks like in one dimension, where we start with experimental data that's truncated, we extend it artificially with linear prediction, and we reprocess it to get a spectrum, which in this case has a line width which is maybe 25 or 30% sharper than the original line width we had. And linear prediction in this form is a one-dimensional function. So in a three-dimensional data set, if we want to use linear prediction in the indirect dimensions, we apply it to all the vectors in one dimension and then independently to all the vectors in the other dimension. And here's one example of a result. This is a carbon-nitrogen plane from a CbCaNH. Here's the original experimental data. And here's what that data looks like when linear prediction is applied in both the nitrogen and carbon dimensions. So you can see we can reduce the line width in both dimensions here by a substantial amount, almost a factor of 2 in this particular case. But there have been other approaches as well, and the one that we'll talk about today is the idea of non-uniform sampling on a uniform grid, or what we will just call non-uniform sampling for short. Now, in any particular indirect dimension of a biomolecular experiment, we most commonly measure data points which are uniformly spaced in the time domain, like we see here. But what we can do is imagine a circumstance where we randomly skip particular points in this data measurement. So we measure over the same range of time, but we measure fewer points. Now, the underlying information is still there. How do we get to it? Well, if we want to apply our usual workhorse, which is the Fourier transform, this happens to correspond to filling in the missing points with zeros. Let's see how that works. So we have our example of non-uniformly sampled time domain data that we want to transform. We've skipped over a certain fraction of points. Here it's half the points that we've skipped over and filled in those missing points with zeros. So what happens when we Fourier transform this kind of time domain data? The mechanism is the same as before. Fourier term, we multiply it by our non-uniformly sampled time domain data, and that generates a product. But in this case, some parts of the product are randomly missing, I'm sorry, I'm having a little problem with this animation. Let's try again. So as I was saying, we multiply the Fourier term by our non-uniformly sampled data to form a product. But since points are missing from this product, we again don't have perfect cancellation between the positive and negative parts. And so the corresponding spectrum seems to have this artificial noise in the baseline, this random noise in the baseline, but it is not at all noise. It is a completely analytical function of which points we measured and which points we skipped over. So let's look at this in more detail compared to the previous cases. In the fully sampled case, we had a nice flat baseline and a sharp signal. In the truncated case, we have an artificially broad signal with regular but very large truncation artifacts. In the non-uniformly sampled case, though, we have a nice sharp line, but we have what appears to be random noise, the baseline. But that is not random noise at all. It's completely deterministic. It's determined by the pattern of points we measured and the pattern of points we skipped. And the bigger the signal is, the bigger these artifacts will be. And the shape of these artifacts will be the same for every signal. But big signals will have big ones, and small signals will have small ones. All of these are sampling schedules, and they all have different corresponding response functions. We're very familiar with this one and this one because we see them all the time. So we don't think twice about the fact that big peaks have big truncation artifacts and small peaks have the same truncation artifacts but smaller. The case for non-uniformly sampled data is just the same. So we can actually take advantage of this idea. We'd like to get nice sharp lines, but without this apparent random noise in the baseline. So we can't use a Fourier transform all by itself. Well, one hint is brought to us by a whole collection of different methods that depend on thresholding. And the idea that we talked about is that for a given signal in the non-uniformly sampled spectrum, we can anticipate exactly what the shape of the corresponding artifacts would be in the baseline. So it's possible for us to choose a threshold which we know will always be larger than these artifacts, because we know more or less exactly what these artifacts are going to look like. So if we choose a threshold, well, one thing we can do is just ignorantly clip everything below that threshold to generate a spectrum like this one. And why would we do that? Well, if we take a spectrum like this one and inverse Fourier transform it, we get a result that looks like this. In other words, it looks a lot more like a fully sampled time domain signal. And so we can use this general idea in different approaches, either to fill in the missing spaces in the time domain data, or to somehow iteratively build up a spectrum directly. One such method that builds up a spectrum directly is called iterative soft thresholding. And this is an approach that was beautifully demonstrated by people there at the SB Grid at Harvard Medical, with software developed by Sven Heberts there, and nicely applied by James Chu and Gerhard Wagner. How does this method work? This method called iterative soft thresholding, or IST. Well, as we talked about before, big peaks will have big artifacts associated with them. And so if we can find a way to reduce the size of the peaks, the corresponding size of the artifacts will get smaller too. So what we'll do in practice is start with a regular Fourier transform version of the non-uniformly sampled spectrum and choose a threshold, a very high threshold, which we can guarantee will always be much larger than the largest artifacts. And we will change the spectrum only above that threshold. And the way we'll change that spectrum is simply to shave off a little bit of the top of this spectrum and move it into an accumulated spectrum over here. So we get a little signal in our accumulated spectrum, and we get a result which is a little smaller above the threshold and exactly the same below the threshold. We don't change anything below the threshold here. All we do is scale down what's above the threshold a little bit. And now we can take this reduced result and inverse transform it back into the time domain and set to 0 any parts that we didn't originally measure and transform the result back. So what does that look like when we actually step through it? We gradually reduce the intensity of the peaks, and that gradually reduces the intensity of the corresponding artifacts. Whereas in the accumulated spectrum, we gradually build up that intensity, but free of the artifacts. So it's very simple, it works beautifully, and as a final step, although that's not shown in this particular little animation, whenever we stop this series of iterations, we can take whatever is left over in the original Fourier data and add it into our accumulated spectrum so that in practice, no signal ever gets left behind in this iteration. Everything that we start with makes its way into the corresponding IST reconstructed spectrum. So we minimize the possibility of losing even the smallest peaks, because at the end, whatever residual is here added back into the IST spectrum. And here's a couple of examples of how nicely that works. Here's a 2D small molecule example. These are 3 versions of the same 2D toxi spectrum. So here's one example of that spectrum measured with 256 increments in an ordinary conventional linear sampling. And if we look at this indirect dimension, we can see particular signals, in this case separated into doublets. However, if we use the same conventional measurement scheme, but measure only the first 128 increments, we have an example that has half the measurement time, but now it has half the resolution too. So we don't get resolution of these dots in the indirect dimension. However, if we take the same 128 increments, but use a non-uniformly sampled scheme to spread them out over the same amount of time, we can retain the original resolution of the data, but at still half the original measurement time. And so what this means is we get to choose a balance of how many points we measure versus, let's say, how many scans we measure per increment. So we can balance signal to noise content with resolution. Here's another example, a 2D HSQC, conventional experiment, a non-uniformly sampled experiment with half the measurement time, but for all intents and purposes, the same quality data. And here's examples that we care about in triple resonance NMR. Here's a collection of 5 different triple resonance experiments, 4 of which were measured in the non-uniformly sampled mode. And so they were reduced in measurement time by 5% in each of the 2 dimensions. So the total measurement time was reduced by a factor of 4 in this case for each of the triple resonance spectra. And what you're seeing here are the corresponding strips in both the proton and nitrogen dimensions for all the residues in this particular protein, which is, of course, the PET protein of biomolecular NMR, ubiquitin. And you can see the results are beautiful. They look like nice conventional spectrum, nicely clean. And because this iterative soft threshold method is so straightforward, there are not really very many complicated parameters to choose. So it's easy to set up, and the results are very robust. So that's my summary for today. I hope it was interesting, and I look forward to your questions and comments today and also next week when we actually see how to use software to achieve results like this. Thank you so much.
Thank you very much. Feel free to chat me questions. Anyone, if you have questions you'd like, I'll pass them on to Frank. You can just chat them right here in the chat window. Chat here. Great. So, yeah, that was great. Very nice and informative. So, I'm not seeing a lot of questions, but some compliments for sure. And we look forward to next week. And yeah, thank you very much. So, with that, we'll wrap up, and we'll see you again next week.
Okay, thanks so much.
Thanks.
Bye all.